And definitely, you know that high school is not here, right? So yes, any questions so far? I think you all deserve. How many I have? Oh, I have only 4. I should have had more. Yes. Meanwhile, you can ask me any questions. So you can share all these things. So yes, maybe let's start from here, right? So yes, and you all are asking good questions. So this is just to promote asking good questions. Yes. Okay. So let's move on and do some calculations, right? Yes. Yes.
You said you are representing a beta plus emission, right?
Yes.
So it is an up part becoming a down part, right?
Yeah.
But then you have a, so it's a up part emitting some particle, but then you have in the D letter, you have a down part emitting a particle, it becoming an up. What's an up? Becoming a down. I don't understand.
Oh.
Should be the opposite. You put the up down, you put down the. Não era para ser o uzinho embaixo e dele lá em cima.
Yes, that's correct. That's correct. So all the symbols do match. Oh, that's another objection here, right? So since the down part, so if you see the charge, what is happening? Negative 1/3 cannot be equal to.
What is the charge of W minus W plus?
Just this one.
One.
Yeah, that's what plus this is.
So it's minus 1/3 becoming minus 4/3. Because anything W plus.
So that's not quite right. That's not
Não
right.
era para ser então só trocar o Uzinho embaixo, botar o Uzinho embaixo do down e botar o V em cima.
Yes, that makes it correct. But I know, see, that's correct. Mas aqui, você não down, embaixo é up em cima. So, estou pensando.
Ah, tá.
So, that can be. Not correct. That's not correct. So let's see if I made a mistake. It's very good. So W plus equals. In all the directions, it's correct. This is correct. So that's. Let's see how see if this reaction is correct. If this is correct. Because this is correct.
Botar.
So this is not okay. I think that I have. This should be. So this is not correct, right? Because of what you said. This is correct. See, so I made a mistake here. I wrote it. Very good, very good. I'm very happy. So, so good. I'll give you these things. We could learn so much from just simple, very good observation. Yes. This is all I wanted. Like, don't accept anything just for the sake of it. Right? So the question, and we made so many mistakes, but we learned so many things. Beautiful. Very good. I'm so happy. Okay, so the idea was to. Okay, so we know what the final diagrams are. Yes. Now let's. Okay. I want to do like a few processes, like purely electrodynamics, purely, not purely, like electrode and then QCD, just to get an idea of this. So the correct answer is A. So if you kept what I had, none of the things were correct. So I had to change the things. But this is correct. This is what I had. So, what's the moral of the story? Just by looking at the Feynman diagram of a process, you can tell if that's right or wrong by using a lot of conservation laws. At the vertex, there are so many conservation laws: lepton number, baryon number, electric charge, and so many things. Yes. And we find the rules for that using the Lagrange. So now going back to the previous. How does this look like? Okay, so for a general process, right? So let's do this as let's do. So this is. It's a simple process, right? Why did I choose this to be the first? Because, like, we know electron repels the other electron, like electron repulsion. But we know this from like classical electrostatics and these kind of things. Well, what is it in quantum field theory? This is it. Right? So, electron is repelling another electron. That's basically how it's. So if I draw the Feynman diagram for this, so let's call these things as and just by looking at the diagram, what's the direction of time flow from that? So usually in particle physics, like this is the direction of time flow. In general relativity, it's this. So because when you write the Minkowski diagram like this, so this is the time. Right? So it's but in particle physics. And since this is this examples were from high school physics. Probably they are not so sophisticated as never mind. So just by looking at the diagram, you can tell. Of course, when they give you the Feynman diagram, they don't give you what's the direction of the time. You'll have to figure out by just looking at it. So this is the case. Alright, so if in any, I think I wanted to write for a general process. So the amplitude of any process, something like this nature, can be written as actually so usually one writes something like a transition amplitude. Always, like you know this one, you read like this, right? So, transition of initial going to final is what. Right? So that involves some integration. Alright, so here the electron is coming and then going here. So we can associate some sort of a current. This is the current. So let's call this J mu 1 because this is the first one. We could have labeled it already. So there's a current because the charge is moving this way. Right? So that is this. So we can call this J mu. So in that case, the transition amplitude is just, so let's read from like there to there. So maybe from here to there. Is by the way, it doesn't have to be GMP. It can be just like this. The textbook I copied it from. There's any other direction. So it doesn't have to be. Let's say okay, next, and then we go. There's the interaction. That interaction comes over square. So Q is the momentum of this, and then this current, which is and it's all integrated over space time. This is the transition amplitude. Right? So when you do the integration, it will give you some delta functions and other things. So delta functions appear at the vertices just to say energy momentum is conserved. So that's what it is. That looks like this in the form. So in a formal theory and quantum field theory, this is what you do. For some four-dimensional data. So this is what is called the invariant amplitude. Or Feynman amplitude. So from here you can just extract this to be mu is so let's see how we wrote this. Let's associate. Maybe I should have given you the list of Feynman rules. I'm just going to write down right there. Here, right? So any incoming particle will have a a vector representing this in A. Since it's outgoing, this will have UC bar. Right? So here bar is not antiparticle, it's just the outgoing. So similarly, you can associate this UB. This is UB. So these are the initial. This is for the external legs. Right? So basically, if something is going internal, if this is external, that's what it is. So in place of this current, what's happening when you go from here to here? So UA, right? So that's why this is for that. If you want to make okay, this. What's the interaction here? Interaction is I, E. That's the interaction. Well, I think it's two. So that's interaction. So here, so this is the so what is JNU? The current is just this times this times this. Right? So that's why this is this. And what's this current? Isn't it? I, E, and this is the propagator. Right? So propagator is for the formula. So these things, what does the ingoing, outgoing, vertex, and the propagator? So what's the propagator in our case? These are the final rules. Right? So these are the final rules, and we derive them from a given Lagrangian. So one of the art that one should master is, if somebody gives you a Lagrangian, how do you derive these things, right? So I think Helen is doing that in the course. So last time we derived, he derived Gluon propagator in the axial gauge. So this depends on the gauge and everything. And you saw last time, it took like 3 hours to just derive this kind of equation for Gluon. So it's hard. But when I do, I just borrow these ideas from there and directly use them. So how do we compute the invariant amplitude? All you have to do is just do this, and then write down the copy from the textbook, what are the rules, and then just put them together. Right? So that's it. All you have to do is just simplify this. So if we did some simplification, this Q is just whatever the energy momentum comes. So you can add those things. What comes here is PA plus this happens. If you plug this thing in here, you get after eliminating all the mu's and everything, mu minus E squared. Divided by Yeah, just substituting for things. Okay, so this is the amplitude for this diagram. This is not just this is not this is not completed. Okay. So, but this can. There's other possibility. What's the other possibility here? Other possibility is it could have made but this doesn't have to be C, but it could be D. So it could have been D. This diagram is also possible. Because all we know is 2 electrons go in, 2 electrons come out. There is no guarantee that this electron is that electron. This electron could have been this electron. Right? So that there are 2 possibilities. So that's another way of writing this diagram. It's the same as just to keep always C up and then D down. We can write this as just a, there is no, they're not like crossing. There's a yes. This is another way of writing. So now for this diagram also, we have to calculate the same process. What happens when we do the same process? So what we are doing is just we are swapping between C and D, right? So we are exchanging. In this, C and D are exchanged. So when we exchange the fermions, their states, their wave functions are anti-commutative. So what happens when we reverse the order? It gets a negative sign. Right? So it looks exactly the same, but see there's a negative sign, right? But slightly. But different. So this is how it goes. I'm just directly going to write the. See if we can get that from this. In this case. So one method, when the anti-commute, so this is one diagram, this is another diagram. See if everything works fine. So we have flipped C and D, right? In place of C we have D, this has stayed the same. In place of D we have C. That's why this negative sign disappears. But here, what is the, look at this, it's better. So what is the momentum of the propagator? It's not PA minus PC, it's PA minus PD, right? Because of this. So yes. Otherwise it looks like they would cancel each other. So we have 2 diagrams. So what's the total invariant amplitude? Is the sum of all these things. So we have to add this with that. If you want, we can call this like lambda mu2, and then this is mu1, and then the total amplitude would be that's the mu. And from here, how do we calculate the cross section? We will have to square this. Maybe so we will have to square this and then sum it over all possible spin states. So it's more involved than simply. We have to average this, which is all the spin states. Let's call this like a bar. This comes to spin it up. By the way, what is the spin of our particles? It's half, right? So this would be just 1 plus 1, 2, 2 times 2. So this is just 1/4 of this spins. This is called unpolarized process. So instead of writing this in terms of like momentum A, momentum B, and momentum D, there are some variables called Mandelson variables. Let's see if I've spelled it right. I have to find it for this one. Yes. So these are STU. This should be so. This is particle physics convention. We could have just stayed with PA, PT, it doesn't make a difference. Just when you see the answer, sometimes you will see this in terms of S, T, and U. What is special about this? There is something called crossing symmetry. Basically, let's say we have some. This is actually crossing symmetry. If we have some process, something like AB going to CD, we can exchange outgoing and incoming particles, but you have to do that anti-particles thing. So this, let's call this as a S process, right? So S channel process. So the U would be just change this to the other one. So we keep A as it is. So we are extending this with this. This is also possible. This is called the U-channel process. Same thing you can do with T. What's the T? So you keep the D word as it is. Let's exchange this. Okay, so what is this, right? So let's say we have something like, let's take a particular example. We have a process like electron going into electronic. It's an S-channel process. People call this like S-channel process, T-channel process, U-channel process, something like this. And if you find the amplitude in one, you can translate that to amplitude in the other by doing this. So if we did this, what do we get here? So we're exchanging these two electrons, but they become antiparticles, right? What is that? So this is a molar scattering. What's that scattering from? Alright, so it's pair creation. So it's pair annihilation and pair creation, right? Annihilation and creation. There's no cute name for that. That's annihilation and creation. And if you did this, what are we exchanging? This will go back. So let me write down this. This is Baba scattering. Baba scattering is electron positron annihilation. So if you know one, we can get the other. So I wanted to, I just want to write down this amplitude in terms of STU. There is no great information inside. So let me do this. So for molar scattering, this would look like and for Baba scattering. So I think there's a so we are just flipping these things, right? Anyway, you don't learn much from this. Moral of the story is, from the Lagrangian, you can find the final roots, and it's very simple. Given diagram, you can calculate the amplitude. It's simple multiplications and things. And you have to write down all the possible diagrams and then do the weighted sum of those things. Right? So that's the total amplitude. And if you write down the amplitudes in terms of these variables, S, T, U, sometimes if you know one process, you can always calculate the other process by changing. See, what are we doing here? So, what kind of process is this from here to here? This was a S process, right? And this is a U process. U or T? S and U, yes. So if you do the S and U, if you flip them, S squared, U squared, it stays the same. Here, S becomes U, U becomes S. Right? So this gives you the, because of the symmetry, so why I spent some time doing this thing is, if we know one of them, we can just directly write down the amplitude for the other one without doing any calculation. So that's why this is called crossing symmetry. Okay, so this is fine. Yes, sir.
What's happening with the gamma matrix that we have in?
Okay, so in the where was in the amplitude I wrote down some gamma matrices and other things, right? So you go ahead, actually this is what becomes. Suddenly we went from all matrices to just some numbers, right? So what happens? So we had something like this, right? Some string or something. If you use, so this is a vector, right? This is a matrix, this is a vector. So if you write down all those things, it just gives you like 2m with the mass of the. So we are doing a matrix multiplication. By the way, so when we do this, what do we get? We get something like, is this correct? We get a column matrix. Oh, okay. So one of them is a bar, right? So maybe it should be like this, right? So now we get this, and that gives us just a number. So that's how this gamma matrices disappear into just the mass. And the mass is just the square of the momentums, the four momentums. So that's how it is. Yes. Any other question? Any other questions? Once we get the idea, so the idea is only just how to write these three matrices and multiply them. That's the whole thing, right? So finding the amplitude is just as simple as that. After that, like, it becomes just boring. You are not going to learn much. So that's why people write computer programs to just do all these things. In fact, there are already like fail calc on Mathematica. It can do lots of these things. And I think those people, like the professional people who do terminology, I know they use something called Big Pythia, this kind of programs, like standard programs. I don't know whether they generate some events or basically this can all be done in simple programs. But it's good to do a few calculations by hand, right? Maybe I will also do the detailed calculation for a few more of these things. In the textbooks, most of the textbooks that I know, they skip lots of steps, like introducing all the steps, starting from the Feynman rules and do all the calculations. for many of these processes, few electro weak and also few QCD processes. For example, you can have like fancy things. An electron scattered by a quark, and then what happens? Right? So all this is possible. This is like a QCD electrodynamics problem. Many fancy things can happen. I'll do a few of these things. But anyway, the original proposal is to, of course, we have to learn all the old ones. And let's move to the next techniques to see how can we simplify these things, right? These three. But using the same method, I want to calculate for the gravitons. Graviton scattering. Right? That can be very complicated. That's done only in the Feynman's book. If you can use the same Feynman rules to do this, that would be fantastic. Another thing is, like, that's the basic, that's the first thing. For example, in the quantum field theory of spacetime, the graviton, there's no loop involved. It's just playing this thing. But we can have any order for the matter. So you put them together. So gravity is classical, that means there is no loop or anything. But matter is quantum, that means you can have many orders of perturbation theory, many Feynman diagrams for the matter, and go through that. That's the quantum field theory of spacetime, in the language of amplitudes. But if you want to really have any quantum gravity, the first question is, that's the one. By the way, for graviton, you could do this. Four gravitons, like two gravitons come, interact and go. If your theory of quantum gravity cannot calculate this, then it's not a theory of quantum gravity. There are so many theories of quantum gravity in the market. They don't talk about the graviton propagator or any of these things. So that means they are not theories of quantum gravity. So this is the. I want to do this using the Feynman diagrams and then see what happens. And later using the techniques, it can be a simple process. That's the thing. So meanwhile, I don't know when I get the next chance, but I keep trying to make this like a simple writing as possible meanwhile. But anyway, the whole idea of these two lectures was to tell you there is something happening, everybody's doing, but it's not so happening here. So if you're interested in those things, you can do it. So we can follow what is happening in those areas of research. So that's the whole point. And you asked very fantastic questions. I don't need to bribe you with the chocolates for asking questions. You're already asking very good questions. I'm very happy with that. Okay, so that's all for today. Thank you. And since there are a few more left, come take it. I don't want to take them.